Hello, everyone. I'm Carly Christensen, the Area Community Relations Director at University House Issaquah. Before we start today's presentation, I'd like to share a little bit about our community. University House Issaquah is a premier retirement community located near the foothills of the Cascade Mountains, where our residents enjoy access to nearby Issaquah shopping centers, as well as beautiful views of the Issaquah Alps and the year-round natural beauty of our 2 courtyard gardens. We are honored to be partnered with the University of Washington Retirement Association, which gives our residents access to classes through UW's Osher Lifelong Learning Institute. Our residents share a passion for knowledge, art, and culture, and a desire to remain active in mind, body, and spirit. If you'd like to learn more, please give us a call at 425-557-4200. And now on to our main event. We are very honored to host Dr. Abby Winter, who will be presenting on Vaccines 101. Dr. Winter is a licensed pharmacist and clinical assistant professor at the University of Washington School of Pharmacy and serves as the director of outreach for the Pline Center for Geriatrics. Abby leads the educational, clinical, and outreach efforts for the UW School of Pharmacy at the Era Living Communities. And now I'll turn this over to Abby. Thank you so much.
Great, thank you. Give me just a moment to share my slides here with you. All right. So as she said, my name is Abby Winter. I am faculty at the University of Washington School of Pharmacy. Oh, my apologies. And I work with Era Living as well to help provide clinical services and oversight for various health-related things for the residents at Era Living. Today we'll be talking about vaccines. And I know vaccines have been in the news quite a bit lately, but we're not going to focus so much on COVID. We will be focusing on how vaccines work, the history of vaccine development, talking about different types of vaccines, looking at trials for how vaccines become approved. We'll discuss efficacy versus effectiveness, and then briefly go over some vaccine recommendations for older adults. So first, we want to understand a little bit about how vaccines work. In order to understand that, we first need to look at how the body fights illness. So when a virus enters the body, it attacks and multiplies, and that causes an infection. The body's immune system then fights off the infection, and it does so with white blood cells, or what we can sometimes call immune cells, and they work together to fight the infection. There's 3 different types of immune cells that we'll talk about. They work to digest the germs, the dead cells, the dying cells, and then they leave behind what we call antigens. The body then sees these as dangerous and sends antibodies to attack them. So we've probably been hearing a lot about antibodies lately. This is kind of how they work in the body if we have a natural infection. So the body produces antibodies that attack these antigens, and the immune system attacks the cells in the body that have already been infected. So there's another way to think of this. I say, picture someone trying to rob a bank. So the germ or the pathogen is the robber, and the immune system is the bank. The security camera catches the robber entering the bank and sets off the alarm. The white blood cells in our body are like the security cameras. They catch the antigen, or I'm sorry, they catch the pathogen when it first enters the body. The alarm then notifies the security guards, and they find and detain the robber. So the white blood cells are kind of like the security guards who tell the antibodies, and they fight off the pathogen. After this happens, the bank then adds more security cameras, hangs up pictures of the robber, they've got a wanted sign up, and we can think of this in relation to fighting an infection as the body creating memory cells to then remember what the pathogen looks like and remember how to get rid of it quickly if we encounter it again. Let's talk a little bit about memory cells. So the first time that our body encounters a pathogen, it can take several days for the body to build up a defense against that pathogen. But then it creates what we call memory cells, so that with future encounters, the immune system remembers that bad guy. It knows how to fight and knows how to protect itself. So if the same pathogen presents again, those memory cells can respond quickly. It's kind of like putting it in a Rolodex. So once that pathogen is presented again, the body searches and is able to quickly fight off an infection, versus not having that memory cell. The body would have to learn all over again what the pathogen is, how it works, to be able to fight off an infection. So when we're understanding how vaccines work, we look a little bit more at vaccines themselves. So with a vaccine, we present the body with a weakened or inactivated or dead version of that pathogen, and the body imitates but does not cause an illness. We call this often an imitation infection. The body then develops a defense and is able to recognize and fight off that infection in the future with those memory cells. So our bodies develop immunity by imitating an infection. We need a supply of those memory cells that are produced by our immune system after vaccination, and they remember how to fight the disease. As we may have learned recently in the news, it can take a few weeks before the body is able to produce the correct amount of memory cells after they receive the vaccine. So vaccines are pretty important, obviously. Many in healthcare consider vaccines one of the greatest breakthroughs in modern medicine. They help us combat deadly illnesses and sometimes even eradicate them. We're often only able to reach the full potential of a vaccine if enough people get vaccinated. So vaccines are generally safe, and often there's really only minor side effects associated with them for the vast majority of folks. You may have heard recently about something called herd immunity. So herd immunity is one way to help protect the general population. So in order to reach herd immunity, enough people have to have been vaccinated or recovered from previous illness, if we're talking about certain pathogens. There are some pathogens where having had it does not protect you in the future, but for some, having had the actual illness does help protect you. And then herd immunity is really only valuable if we have no human source for spreading the pathogen again. So enough people need to have developed protective antibodies against future infection. And herd immunity helps protect those who cannot be vaccinated. So in some cases, young kids cannot be vaccinated against certain pathogens. Or people who have weakened immune systems, or maybe are not don't qualify to get a vaccine. By having other folks in the community vaccinated or having had illness in the past for certain pathogens, that helps protect our most vulnerable members of our community. So when we talk about eradication, technically, we only have eradicated one disease, which is smallpox. But to put this in perspective, a smallpox vaccine was first developed about 225 years ago, and it took until 1980 for the WHO to declare smallpox eradicated across the world. We are extremely close at eradicating polio. It's been eradicated in certain areas, but not worldwide. And other things that are nearly eradicated: diphtheria, bacterial influenza, measles, mumps, rubella, tetanus, and pertussis. So when we say nearly eradicated, we could say it is in certain places, or the case counts are so small that we're considered very, very close. But as you may have heard in the news in the last however many years, 5-10 years, we're seeing increases in some case counts for things like measles, mumps, rubella, things that are preventable with vaccination. But if folks don't get those vaccines, then we don't have as much protection. Or if one case is a breakthrough, it's easier for it to spread when folks are not vaccinated. So even though things may be close to eradication, that vaccine is still very important. So next we'll look at the history of vaccines. So here's just an overload of vaccine development. I'm not going to go through all of this, but it just shows you how we started back in the 1700s with human vaccines and are consistently adding more vaccines to the mix. As we've seen recently, we have more COVID vaccines that have come out. and even another pneumonia vaccine that came out this summer. So we'll talk about those in a little bit. But first, let's talk about the history of different infections. So back in the 1500s, we saw what we often will say is our first smallpox epidemic, or the first instance of it. We also had a whooping cough epidemic in Paris. And in the 1600s was when we saw the earliest English case of typhoid fever on record. We had a Spanish diphtheria epidemic, and early smallpox came to North America. So inoculation, some say, started as early as 200 BC. While it wasn't the true vaccine as we think of it today, there are some sources that claim that there were inoculation-like practices where Buddhist monks would drink snake venom to try to provide immunity from snake bites, which is kind of the idea behind a vaccine. In the 1600s, we had a Chinese emperor who survived smallpox as a child and then had his children inoculated, and they did so by grinding up scabs from smallpox wounds and blowing them into the nostrils of other people. Another way they would do this is they'd scratch the matter from those smallpox sores into the skin. So it's a way to introduce it to someone who has not had the disease, but in a small amount in order to try to get the body to develop an immune response. In the 1700s, there were reports of something that they called an operation, where they'd place a small amount of smallpox matter on the head of a needle and inject it into the vein. But in 1774 was when we started to really see something that resembled the more modern day vaccine, where there was a farmer who inoculated his family with cowpox, which then protected them from smallpox. So cowpox and smallpox are different, but because they are somewhat related, it was able to mount a response in these individuals so that they were not as susceptible to getting smallpox. So where does that word vaccine come from? The cowpox virus contains the vaccinovirus. And so we use that name of the virus to coin the term vaccine, because cowpox was kind of the first introduction to what we consider vaccines. So now let's talk a little bit about different types of vaccines. We'll go through each one, but we have live attenuated, inactivated, toxoid, recombinant or polysaccharide or conjugate vaccines. Things we've become cursory experts in lately are DNA and RNA vaccines and our viral vector vaccines. So first, live attenuated vaccines. These contain a weakened version of a living virus or bacteria, but it does not cause serious disease in people with healthy immune systems. These live attenuated vaccines are very good teachers for the immune system, and they're the closest thing that we have to natural infection, which provides very good immunity for most pathogens. Some examples of our live attenuated vaccines are the MMR vaccine, which is measles, mumps, and rubella, the varicella vaccine or chickenpox vaccine, which many people, if our older adults especially, have not received because they had the actual disease. But our younger kiddos are now getting that chickenpox vaccine. Yellow fever is another live attenuated vaccine, rotavirus, and then the old shingles vaccine. So there's a new one that came out a few years ago, which we'll talk about in a little bit. Next is our inactivated vaccines. So inactivated vaccines contain an inactivated or dead form of a pathogen. This produces a different type of an immune response than a live vaccine does, but it's still a very good protection. It often requires multiple doses, though, to build or maintain that immunity. So some examples of our inactivated vaccines are inactivated polio vaccine or IPV, our rabies vaccine, and hepatitis A vaccine. Next, we'll talk about toxoid vaccines. So toxoid vaccines prevent diseases that are caused by bacteria that produce toxins in the body. So these vaccines create immunity to a part of the pathogen that causes the disease, rather than creating immunity to the pathogen itself. We have toxoid vaccines that contain weakened toxins, which are called toxoids, and they cannot cause illness, as we'll see as a common theme with our vaccines here. When exposed to a toxoid, the immune system learns to fight off the natural toxin. So the best example of this one is the Tdap or Tdap vaccine, which has diphtheria and tetanus toxoids in it. Next is our recombinant, subunit, polysaccharide, and conjugate vaccines. So there are different types, but they all work very similarly. So we'll talk about them together. These types of vaccines use pieces of the pathogen. So an example would be a protein, or maybe there's a sugar casing around that pathogen. So they use that piece of the pathogen in order to help create an immune response. The vaccine targets that key part of the germ, and it results in a very strong immune response because it's very targeted. It is safe for those with weakened immune systems, but we do often need booster shots to get that ongoing protection. So lots of examples here: the HIV disease, which is a different type of influenza infection, hepatitis B, our HPV, which is human papillomavirus, whooping cough, which is also called pertussis. That's the P in our Tdap or Tdap vaccine. Pneumococcal disease, meningococcal disease, and the new shingles vaccine are all considered this type of vaccine. Next, our DNA or RNA, or more recently, what we've been learning about is our mRNA or messenger RNA vaccines. So this technology is actually decades old. They've been studying it for quite a while, but it's the vaccine development itself is a little bit newer. These vaccines make proteins that trigger an immune response, and it provides the cells in the body with instructions on how to make an antigen. And as we talked about earlier, we have that antigen that then tells our body to attack kind of an outsider. The one really good thing about these mRNA vaccines is they have a much shorter manufacturing time, as we've seen in the news lately with our COVID-19 vaccines. They also have no risk of causing disease. The way that this mRNA is introduced into the body, it helps produce a response, and within about 72 hours, the mRNA completely dissolves and leaves the body. So then the body just has those instructions on how to create that response. So currently, our only example of the mRNA vaccines is with a couple of the COVID-19 vaccines that are on the market now. Next is our viral vector vaccine. This one's a little bit newer too, but it uses a modified version of a different virus as a vector to deliver protection. So some viruses that it'll use are influenza virus, VSV, measles virus, or adenovirus. Sometimes these have a possibility of being a little less effective if the person getting inoculated has been exposed to that vector virus in the past, but it does provide pretty good protection. So scientists have been studying these types of vaccines for decades as well, but currently the only example is some of our COVID-19 vaccines that are available in the world. They are using this technology to study vaccines against Ebola, Zika, HIV, and a different type of flu vaccine. So we may see more of these in the near future. Next, we'll talk about vaccine trials. So here's a brief overview of how vaccine trials work. With safety testing, it's important to know that vaccines are held to very high safety standards. So there is a lot of testing that's done before a vaccine is approved or recommended by various governing bodies. And we do lab testing, which often can take years. And then we determine if it's okay to test it on people. There's then ongoing testing and testing and observation after a vaccine has been approved, which is very common practice. So we're constantly assessing before and after approval. So first with vaccine development, there's many different stages. We start with exploratory, then move to preclinical trials, clinical development of the vaccine itself. Then there's regulatory review and approval by places like the FDA and CDC recommendations. And then we continue with manufacturing quality control. So with our clinical trials, this is where we evaluate safety and effectiveness with human volunteers. So we answer the following questions. Is the vaccine safe? What dose is best? How does the immune system react to the vaccine? And with our clinical trials, we have multiple phases. Phase 1 is where we start with just a small group of healthy individuals. usually 20 to 100 people. And once it's proven to be safe in those individuals, we move on to phase 2, where we expand our population and look at patients who maybe represent the intended, what we'll call audience. So if we're trying to look at a particular disease we're trying to prevent, we would then expand it to folks who would be more likely to encounter that. With phase 3, we then look at thousands of people and test for efficacy and safety. And then phase 4 is our ongoing studies after the vaccine is approved or licensed, where we continue to monitor, because as we go from thousands of people to hopefully millions, there can be some other things that come up. And so they just keep an eye on that stuff to make sure that we're keeping our population safe and the vaccines are still safe and effective. Vaccines also undergo quite a bit of testing. So as I've alluded to, once they're approved or authorized, that testing does not stop. So every single batch of vaccines that's created undergoes testing for multiple things, including potency. So that test, does it work like it's supposed to? Does it provide the benefit that we hope it provides? Is it as strong as it's supposed to be? We look at purity, which helps us ensure that certain ingredients that are used during the production of the vaccine are removed before it is produced and utilized in humans. And then sterility. So is it sterile? We ensure that there's no additional outside germs present. The FDA also tests the factories where the vaccine is made for different quality and safety standards. So every vaccine that's out there today, wherever it's being produced, they're constantly undergoing tests through the FDA, just to make sure that everything is up to code and safe. So we also track side effects for vaccines, and folks may have heard about this a lot more in the news lately. Our Vaccine Adverse Event Reporting System, or VAERS, is what often it's referred to as. This is a national vaccine safety surveillance program that's co-sponsored by the FDA and the CDC. So it helps collect, analyze, and analyze information from various adverse event reports, and then takes that information to decide whether or not we continue to offer these vaccines, whether additional warnings need to be associated with them, that type of thing. So just because there's one report of a side effect does not mean we suddenly stop production, doesn't mean we suddenly stop giving these vaccines. It gives the FDA and the CDC time or notice that maybe we need to look into something. But it is important that we realize that multiple different groups of people can report to VAERS. So it's both, I would say, a good and a bad thing that it's open to anyone, because patients can report any side effects they have, providers can report side effects their patients have had, parents of kiddos can report, pharmacists and vaccine manufacturers can all report. But while this is great because it opens it up to the community and any potential side effects gets reported, there's also a high likelihood that side effects are reported that may or may not be directly related to the vaccine. So maybe I get a vaccine and 4 days later I get some terrible rash, or maybe that's when I'm suddenly diagnosed with a new illness or something like that. It would be easy for me to say, oh, I just got this vaccine, this is related. But there's also a very high likelihood that what I developed may not have been related to the vaccine. So that's why it's important that we report it and give the FDA and CDC time to assess all of those reports to determine whether or not it is likely that it was related to the vaccine, or if there's enough people reporting similar side effects, whether or not that is actually related to the vaccine, or if the likelihood is similar to, more than, or less than what the general population experiences. So we take all of this with a grain of salt, but do have some peace of mind knowing that there's ongoing reporting happening with these. So it's not like they just get approved and then suddenly we're done. This is available for all vaccines. So next, we'll look at the efficacy and effectiveness of vaccines. So they sound like very similar words because obviously they are, but they do mean different things when we talk about them. So when we're reading in the news or trying to decipher what these scientific reports are talking about, efficacy and effectiveness are two different things. So efficacy is the percent reduction in disease incidence in a group of vaccinated people compared to a group of unvaccinated people, but this is only if it's under ideal and controlled conditions. Effectiveness looks at the ability of a vaccine to prevent the outcomes of interest, so perhaps the disease incidence, or could be death or serious illness, in the real world. So we measure this in our observational studies. So with efficacy, when we're looking at ideal conditions, we're looking at folks who have no other chronic conditions. They got all of their doses on time. They did not miss any doses. Most of the time, they're not on any other medications, and their side effects were monitored very closely. It often does not include those age extremes as well. So we don't have the super young kiddos or our older adults. So when we're looking at optimal conditions in our studies, it doesn't really look like the real world, right? How many people do you know that aren't on any other medications and don't have any other chronic conditions, and are very good about getting everything exactly on time as they're supposed to? Not many. So when we're looking at our ideal or optimal conditions, that's efficacy. But effectiveness looks at the real world. So there's so many different things that can impact effectiveness. When we look at the patient themselves, their age can play a role. If they have other chronic health conditions, if they've had prior exposure to a pathogen, that can impact how well the vaccine may or may not work. How long it's been since they were vaccinated can also play in. The vaccine itself can differ by how it's delivered into the body, and that can impact its effectiveness. The type of vaccine, so if it's a live vaccine or an inactivated vaccine, it has a different implication with effectiveness. And what the vaccine is made of can also play a role in different patient populations. Additionally, with some vaccines, it's important that we see whether or not the vaccine matches the strains or different variants that are circulating. So we often think about this with the flu vaccine, where every year we assess what vaccine strains, what flu strains are circulating around the world and which ones are most likely to cause or have the biggest impact in our country. And that's how we develop the flu vaccine. Currently, we're thinking a lot about variants with the COVID and how our vaccines will hold up to those variants that are circulating. So a couple of things to consider. The flu vaccine efficacy varies from year to year. It's anywhere from 40 to 60%. And that's interesting to think about because often when we are looking at these COVID vaccines, they initially came out over 90, 95% effective, and that was really great. And then as we're starting to see maybe in the real world, it's a little less than that, or the one that was 92% effective versus 96% effective, people were a little hesitant. But with that 40 to 60% efficacy in the flu vaccine, it still saved thousands of lives every year. So it's important to have a little perspective. Also keep in mind that no vaccine is 100% effective. So the FDA, when we were assessing our COVID vaccines initially, set a 50% efficacy cutoff for emergency use authorization of those COVID vaccines. So all that had to be shown was that it prevented disease or decreased the severity in at least 50% of people who were vaccinated, and that was going to be an incredible outcome. So the fact that we reached over 90% efficacy for or effectiveness for a lot of our vaccines was really, really wonderful. So just kind of keeping that in mind, if we start to see effectiveness out in the real world should be less than that 90% that we saw before. It does not mean the vaccine is not good. It does not mean it's not working. Next, let's talk about vaccine recommendations for older adults. So over on the right, you'll see the ones that we're going to talk about today that we deem to be most effective and recommended for older adults to make sure that we're keeping them as healthy and preventing disease as much as possible. As we age, our immune systems do weaken over time, and this can make it a lot more difficult to combat different infections. It's also important to note with older adults that our susceptibility to complications from various preventable diseases can increase. And so vaccination is an incredibly effective way to help reduce complications from diseases, to help prevent diseases, to help give our immune system a little bit of a boost when it can decrease over time. So first, we'll talk about shingles. The Shingrix vaccine is what helps prevent shingles. And for those of you who are not familiar, lucky you, but shingles is a very painful skin rash that's caused by the virus that's also responsible for chickenpox. So if you've had chickenpox in the past, you are at risk for developing shingles. That virus remains dormant, kind of goes to sleep. And if different things trigger it, the biggest thing we think about is a big stressful event that can sometimes trigger that virus to come back and wreak havoc in the body. Who should receive this vaccine? All adults 50 and older, according to the CDC, are candidates for this vaccine. There are other people who may get the vaccine with different immune conditions or on certain medications, so talk to your doctor about that. But good thing to note, there is no maximum age for the shingles vaccine. The Shingrix vaccine is 2 doses, and it's separated by 2 to 6 months apart between the doses. And it is more than 90% effective in studies, so that's really great. And these vaccines are often available at your pharmacy, or depending on your insurance, you can talk to your doctor's office to see if they have them available as well. Next, we'll talk about the pneumonia vaccine. So currently in use, there are 2 different types of pneumonia vaccines, Pneumovax 23 and Prevnar 13. The number relates to how many different serotypes they fight off. And there is a 3rd vaccine for pneumonia that was approved this summer by the FDA with a fast track approval. This one is called Prevnar 20. The CDC still needs to weigh in to form their recommendations about its use and when and who, but it's currently approved for adults 18 and over. But we don't really have a timeline right now for when it will actually be available out in the world, but do know that that is approved and may be on the horizon. So pneumococcal disease can cause different types of, can present in different ways, cause different types of infections, but often they can be infections throughout the bloodstream and the organs, and it can be pretty serious and deadly for our vulnerable populations. Who should receive this vaccine? All adults 65 and older. There are younger kiddos that also get it. And then those who are adults age 19 to 64 may also be a candidate for a pneumonia vaccine if they have other chronic health conditions that put them at risk, or if they are a smoker, because we know that the complications from different pneumococcal diseases can be worse in folks who smoke. As we mentioned, there are 2 different types of pneumonia vaccines. They're intended for different populations. Knowing which versions of the pneumococcal disease and pneumonia are more prevalent in different populations. So talk to your doctor about that, and they'll be able to give you recommendations about which one is best for you and when you should get it. Next is influenza. So we also call this the flu shot. This is pretty timely because we're coming right up on flu shot season. So influenza, or the flu, is a viral infection of the lungs, nose, and throat, and it can be deadly, especially in our high-risk individuals. High-risk individuals we often think of as our older adults and our super young kiddos, folks who may not be able to receive the vaccine, like those under 6 months old. Who should receive this vaccine? All people 6 months of age and older. So the flu shot is a really great way to help prevent serious illness. It saves thousands of lives every year. So even though flu may not be on our radar as much lately, especially after last year when our masking and social distancing from COVID did a great job at preventing flu from spreading, it's still incredibly important that we get a flu shot every year. It is a seasonal vaccine. This is anecdotal, but we're currently not quite sure what to expect from this flu season. There's some anecdotal reports from various physicians who believe we could be in for a pretty deadly flu season this year because we didn't have a lot of flu last year. So as we're seeing in some of our young kiddos, RSV and different viruses that often show up in the winter time, we're starting to show up this summer once things opened up again and people stopped wearing masks as often and we were a little less vigilant. All those things we normally see in the winter that we didn't see, we're starting to show up in the summertime. So we're a little bit worried that flu could be the same way, where it didn't show its head as much last year and now it's going to be even worse. So that's especially important to get your flu shot, but also maintain those important practices that we've been doing, like hand washing and that sort of a thing, to try to prevent these diseases from continuing to spread. Next, we'll talk about our tetanus, diphtheria, and pertussis vaccine, or Tdap. You'll also see this as Dtap or TD. Each letter stands for a different pathogen. And if it's capital versus lowercase, it means different things too. But for the most part, you just need to know which letters are involved. But Tdap is the one that's most prevalent. So tetanus, diphtheria, and pertussis are all serious illnesses that are preventable by a vaccine. So it's important that we get these vaccines because if we can prevent something, we should try. Diphtheria and pertussis can spread easily from person to person. And tetanus, as you may be familiar, can enter the body through different cuts or wounds, like stepping on a nail. We always talk about going to get your tetanus shot. So who should receive this vaccine? All adults should receive it. And then booster shots are recommended every 10 years. We also recommend a tetanus shot if you have a serious cut or wound. So like we said, you step on a nail or you get a cut from something rusty that you don't know what's on it. A tetanus booster is a good idea, especially if it's been more than 10 years, just to make sure that we prevent those diseases. And then we also recommend a booster for our Tdap vaccine if you may be planning to be around a newborn baby. So we try to get that herd immunity protection for our young kiddos who cannot be vaccinated against pertussis. The pertussis is also called whooping cough. That's that P in the Tdap vaccine. So when kiddos can't be protected from that, if we protect everyone who's around them or spends a significant period of time around them, we can kind of create that wall of immunity to help protect the young kiddos from the serious illness. And then the last one we'll talk about today is our COVID-19 vaccine. So we've been overwhelmed with information about COVID vaccines lately, so I'll just briefly touch on it. I will say I am not an expert in COVID vaccination, so I don't want to try to come off as one. However, I do make sure to utilize the resources and refer to the experts when coming up with recommendations and gathering information about this stuff. So while I, even as an educator and a scientist myself, I could read all the studies and try to interpret that data, I tend to try to trust those who have already interpreted the data and come up with what these recommendations are. They've devoted their lives, their professional lives, and millions, billions of dollars to study these things and come up with the recommendations that are shown to be best for our general populations. And rather than trying to do my own research, I like to rely on the research that these experts have done and the recommendations they've come up with. So with the COVID vaccine, SARS-CoV-2 is an infectious disease that's caused by this newly discovered coronavirus that we're unfortunately all too familiar with. It can cause respiratory illness that can spread from person to person through respiratory droplets. And as we've seen, it can be deadly, especially so in our vulnerable populations like older adults, immunocompromised individuals. And it's important that we receive the vaccine if we are eligible. So all people 12 years old and up should be receiving a COVID vaccine. There are very, very few contraindications. So it is incredibly unlikely that someone would have a true health condition that would make them not a candidate for this vaccine. We're even seeing recommendations that all pregnant women, breastfeeding individuals, folks who are maybe trying to get pregnant, all of the organizations affiliated with those things are recommending vaccination. As we've seen, our older adult population is incredibly important that they get vaccinated because they can be at highest risk for some of those serious complications and deaths from COVID. Most people with underlying medical conditions can receive the COVID vaccine without much issue. As hopefully others who have received it can attest that while the symptoms for a day or two after may be a little bit rough, it's nowhere near the potentially detrimental effects that we can see from the actual virus causing illness in folks. So there are currently 3 vaccines in the United States that are approved to help with COVID, and all of them are recommended for use in older adults. So we covered quite a bit of information today. I'm happy to answer any questions that may come up. And if you're unable to type those in today or show your video to share those today, I'm happy to receive them via email as well. If you reach out to Era Living, they'll be able to get us connected. So thank you for your attention today. I appreciate it. And I'll hang on in case any questions come up.
Thank you, Abby. We'll give it just a moment in case we have any questions that come up, but just want to thank you for your incredibly informative presentation today. And then just remind folks as well, if you have any questions about University House Issaquah or you'd like to tour the community, you can give us a call at 425-557-4200. I don't see any questions popping into the chat, so we'll go ahead and conclude today's presentation. Again, my name is Carly Christensen. I'm the Area Community Relations Director here at University House Issaquah. Thank you everyone for being here and have a wonderful day.